Welcome to 9.2 Sound Waves on the Move. Now, we've already decided that sound is a compression wave. We have areas of rarefaction and areas of compression, rarefaction, compression, area of rarefaction, etc. So what this means is that in order for sound to be conveyed from one place to another, there needs to be a medium, a substance in the middle that will allow itself to be compressed and to undergo rarefaction. A good example is air. So air certainly allows the particles to come together closer, to be compressed, and then to be undergo rarefaction. But for example, we might have a solid wall here of lead or something, and this lead wall doesn't allow itself to, be compressed at all or to undergo rarefaction. So that might mean that it doesn't transmit sound that well. Another example would be, for example, a vacuum in space. It might be that we can't transmit, can't compress or have the particles undergo rarefaction because there simply are no particles there in the first place. So that certainly would mean that the sound wouldn't move through that area very well. In fact, you can't hear it all in space because there are no particles. So the sound moves through materials more efficiently when they're quite elastic. That is, when the particles are able to, undergo this compression and then rarefaction, then compression, then rarefaction very easily without losing a lot of energy. So air is a good example of it. But for example, a brick wall is not, although the speed at which the particles might move through there would be relatively fast because they're all very close together, it's not very good at transmitting that sound because this wave of compression and rarefaction isn't very easy with a brick wall. It doesn't, bend and stretch that easily. So let's have a look at some speeds of sound. Okay, so what we've got here is a variety of speeds of sound in various substances. So this is carbon dioxide, and carbon dioxide is 260 meters per second, whereas normal kind of dry air is 330. So you can see carbon dioxide, it moves through carbon dioxide a bit slower than it otherwise would. And on the other hand, with hydrogen, it moves through rather faster than water. And as we move down, the particles are kind of ending up being closer together, so the sound can move through it faster and faster. But remember what we said. What we're really after here is not the speed of sound to increase, but its ability to be elastic and to move from being rarefied to compressed, to rarefied to compressed, to rarefied to compressed. But this knowing about the speed at which sound moves through an object is really quite important. One good example of this is sonar. Sonars used by ships to map the ocean floor, detect schools of fish, and locate other, underwater objects such as shipwrecks and submarines. So if you send out a high-frequency sound, what you can do is you can measure the amount of time it takes for that sound to return all the way to wherever you sent it from. So the amount of time it takes will mean that you'll be able to map basically the bottom of the ocean. So let's see if we can draw a small picture here. So let's imagine there's some object like this on the bottom of the seafloor. Okay. And you send down these waves. You notice that the sound wave that comes up like that is going to take longer. These ones are going to take longer to get all the way back to the surface than this one. It's got less distance to travel, yeah? And this one's got longer to travel, and this one's got less to travel. This one's got longer to travel again. All right, for it to get all the way back up, this one's got longer to travel. So by doing that, by calculating the amount of time it took for each of these sound waves to return to its source, you can kind of get a map of what the ocean floor is like, and that's used not only by humans in regards to sonar, but also it's basically what echolocation is. And echolocation is by whales, dolphins, bats, etc., to sense their surroundings. You hear about bats being blind. Well, they determine their environment very much by echolocation, sending out a screech and then having some idea of what's going on around them. Another brilliant application of sound in the very similar kind of way is ultrasound. Ultrasound is basically just echolocation. It's exactly the same idea. You're sending a sound through a woman's belly into her womb, and you detect, how quickly the sound returns to its source. So you can, this is a ultrasound of a child. See the head here, the ears, and the spine and back and all the rest. But it can also be used to look at things like, look at cancers and kidney stones and gallstones and whatever else. So that's chapter 9.2, easy peasy, Japanesey. What you can do now is put the blue words into Quizlet, and I would like you to also answer questions 1 to 6. Questions 1 to 6, and put the blue words into Quizlet, and I'll talk to you in class. Okay, bye.